This is the last section we're going to do in Chapter 7, Section 7.4, the hyperbola. So as with the ellipses, we're going to first analyze hyperbolas with the center at the origin. Because then we have the simplest form. And then we need to find a feature of hyperbolas called the asymptotes. So you'll see these are quite different than the vertical asymptotes we found with rational functions. They're going to be slanted. So we need to be able to find the asymptotes of a hyperbola because they help us draw it correctly. Then we're going to analyze hyperbolas with center at HK. So you'll see what you already learned about ellipses is going to match up, so you don't have to learn a new thing about the center. And then there's going to be the applied problems. And again, we probably won't have time to do any applied problems in class, so you'll have some in your homework. If you have trouble getting started, feel free to ask questions, but we're not going to have time to do any in class. So let's talk about the definition of a hyperbola and see how it's different from the definition of an ellipse. When we had an ellipse, we talked about the distance from a focus to a point on the ellipse to the other focus, that the sum of these two distances stayed constant and was 2a, the width of the whole ellipse. Well, when we're talking about hyperbolas, if you go to a point on the hyperbola and you draw a line to one of the focus points and you draw a line to the other focus points, turns out that this difference in the distance is what stays constant. And I have an interactive figure here to show you how that works. So it's a collection of all points in the plane, the difference of whose distance from two fixed points called the foci is a constant. So there's names for the parts of the hyperbola. The conjugate axis is the one the hyperbola is symmetric about this way. The transverse axis actually cuts through the hyperbola. It cuts through focus, vertex, center, vertex, focus. So that pattern's different than the ellipse, but everything still lines up along a line, and that line's called the transverse axis. We have a center. That's a point not on the hyperbola, but it just helps locate the hyperbola. We have points called vertices that are points on the hyperbola. These are, again, extreme points, but now these are the closest points to the center, whereas on the ellipse, the vertices were the farthest away points from the center. Then the foci are important points here that make the shape of the hyperbola what it is. If the focus point's very close to the vertex, the hyperbola is very flat. If we pull the focus way out here, then the hyperbola is much deeper and narrower. Then we also have something called the asymptote. So these are going to be two slanted lines that give us the shape of the hyperbola. So those are going to be the asymptotes. Then the branches, each piece of the hyperbola is called a branch or an arm. So we'll first look at a hyperbola with a transverse axis along the x-axis. But again, I'm going to show you that I don't really think of these as two completely separate things. They're very much related. And so really all the things you learn about one apply to the other. So this is the case when the transverse axis is the x-axis. So you know the hyperbola has to go this way because the transverse axis has to cut through the hyperbola and go through focus, vertex, center, vertex, focus. So the equation, because the transverse axis is going in the x direction, the x squared term comes first. So that's going to be the only difference with the hyperbolas, is that the order matters because there's subtraction. So with the ellipses, it was addition, so the order didn't matter. But now we're doing subtraction, so the order matters. So now I want you to notice that we have a little c again, and c is still the distance from center to focus. Yay! It's the same definition. But now see how the focus point needs to be inside the hyperbola. So if the vertex and c were the same number, c squared would equal a squared. But the focus needs to be farther away, so it's going to be plus b squared. So see how this is the sum of the denominators. So the hyperbola formula has a minus, so the c formula has a plus. That's just the way I help myself remember. But the thing that's the same about the ellipse is under the x number, you will find a number that tells you how wide the hyperbola is. Under the y number, you'll find a number that tells you how tall the box is, and you'll see in the next step we're going to make a box that helps us actually draw the hyperbola. Okay, so then the other type of hyperbola is, what if the transverse axis is along the y-axis? So then I have focus, vertex, center, vertex, focus. And if the y-axis is the direction of the transverse axis, then the y squared terms comes first. And you can check this by seeing, let's see, the vertex has to be a point on the hyperbola. So the equation has to be true if I put 0 in for x and a in for y. And you can see that if the terms were in the opposite order, it wouldn't work. So go ahead and try that. So you see that vertex points are on the graph, so that means they have to make the equation true. Keep going back and forth between equation, graph, both have to be true. Okay, so now let's look at the asymptotes of the hyperbola. So a hyperbola has two oblique asymptotes. And again, I'm not going to do a lot of memorizing of formulas. I'm going to draw the picture and figure out what the equations of the lines have to be. So I don't actually memorize these two formulas. You can if you like and if that makes sense to you, but that's not how I process hyperbolas. So I would look at this equation and I would say, let's see, I look under the y and I see that the hyperbola, I need to go plus and minus 4 in the y direction to get to the vertex points. And I know the y comes first, so I know the transverse axis has to go in the y direction. Then under the x squared number, I see 4, so I make the same two dots that I made for the ellipse, but now the way I use the dots is different. So I still can make a box like this, and if this equation had a plus and it was an ellipse, I'd be ready to draw it. But since it has a minus and it's a hyperbola, we actually draw the two diagonal lines that go through the opposite diagonal corners of this rectangular box that we've made. And they should intersect here at the origin, so pretend they do. But now I can write the equation of this line because I can see that the slope is up 4 over 2. So the slope is 2. So the equation of this line is y equals 2x, since I can see from the picture that the y-intercept is 0. But now let's think about what's the slope of this line. Well, it's up 4 and backwards 2, so the slope is negative 2. And this is always going to happen if you think about the symmetry of the hyperbola. So this line has the equation y equals negative 2x. So the center, this one's a simple one where the center is 0, 0. The transverse axis is the y-axis. We see the vertices. Not yet, because we need to draw the hyperbola. So the hyperbola needs to approach the asymptotes, touch the vertex, and approach the asymptote. Approach the asymptote, touch the vertex, and approach the asymptote. So now we've drawn the hyperbola and we can see where the vertices are, 0, 4, and 0, -4. So now let's see how we find the foci. C squared now is going to be the sum of the denominators, so the order of them doesn't matter at all. So C is going to be plus or minus 2√5, which is going to be between 4 and 5. So I know that 1, 2, 3, 4 gets me to a vertex, so I need to go a little farther to get to a focus. 1, 2, 3, 4 to get to a vertex. So here's a focus. So let me get rid of this V that's in the way. Put it up here. I almost always have to erase my letters and rearrange them. Not a big deal. Just erase, put them where they make sense. Okay, so the focus points are 0, 2√5 and 0, -2√5. So we've done everything. We've got the asymptotes and we made the graph. So let's look at number 36 in class together. And we'll make another movie to look at this second part.